Assalamu alaikum everyone. Welcome to the fundamental design of the concrete. Today we're going to cover only four topics: stress strain diagram, modulus of elasticity, modulus of rupture, cracking moment. Watching this video, I assume that you guys already know mechanics and statics. So mechanics, statics, and strength of material is a prerequisite to the concrete design. So let's start talking about the concrete. Starting with the stress strain diagram, right? From the behavior, you can see, from the diagram, sorry, we can see that it's going elastic and turns into, or linear, and then turns into non-linear or inelastic. Actually, this, from the graph, you can tell that the concrete is brittle, and that means it's not ductile, right? Here we have the stress, and here we have the strain. That's okay. So what does it mean from the graph telling us, what the graph is telling us? The graph is telling us that regardless of the strength of the concrete, because FC prime indicates the strength, regardless of the strength of concrete, the concrete can reach an ultimate strain of 0.002. 0.002 is the compressive strain, is the ultimate strain of the concrete. And here, 0.003 is where it ruptures. All right, between 0.003 and 0.04. For this course, we're going to consider it as 0.003 is the strain rupture of the concrete, and 0.002 is the ultimate. These two figures are really important to remember while designing, because we're going to use it a lot, and we're going to see how. Now, the first aspect, as we said, is talking about the stress strain diagram. The slope of the diagram is actually called the modulus of elasticity, which is symbolized as E. Stress over strain. Now, the modulus of elasticity has an equation given by the scientist or the code, which is equal to, if you talk about US customary units, 57,000 radical FC prime. Right. So US customary units, the code, so the unit will be pound square inch. This is US customary. If we're talking about in the SI unit, so E is equal to 44,700 radical FC prime, and the unit will be megapascal. This is SI unit. So what does it mean? It means the more FC prime, the more strength the concrete have, the more modulus of elasticity it will have. What does it mean? It means actually that the material will have more resistance, it's more durable to take the load. That's why when you go to high-rise building, the engineer will specify a very high number of value of the FC prime. Usually the FC prime ranges between actually 3,000 to 4,000 PSI for FC prime for normal concrete. But for high-rise or for high-strength concrete, we usually go to 6,000 PSI. Actually, if we're going to talk about in SI units, we'll talk about from 28 megapascal, I think, to up to 40. Even it can go up to 90 or 60 megapascal. Right. Then I'm going to talk about what does happen actually when you load the concrete. When you load the concrete crushes actually from the bottom, from the tension side. So the concrete is strong in compression but very weak in tension. This is where the code introduced something called modulus of rupture. It's actually the flexural tensile strength of concrete obtained by when the concrete is loaded. It can be specified or tested in the lab by split test as per the ASTM code. So finally, the ACI 318 is giving us the formula of the modulus of rupture as 7.5 radical FC prime in US customary units. So that will be PCI, or it will be 0.7 radical FC prime. That's in SI unit. So this will be in megapascal again, and this will be in PCI. So what does it mean? Actually, quickly saying, it means if the stress in a beam exerted by the load, right, is less than its property, which is the flexural property of the concrete, that means we will not have any cracks, no cracks in the beam. And if the stress exerted by a load is higher than or greater than the flexural, that means the concrete or the beam start to have to obtain cracks. We will see this in the other slide, actually, when you talk about the M crack. Right, talking about the M crack here again. M crack it means when the concrete starts cracking. Right. So at the beginning, when you load the beam here, let's take this diagram. When you load P, let's take the load P. At the beginning, the concrete has a stage called uncracked stage, where no cracks will occur. But with time, when we increase the load, the moment will start when the moment of the load exerted by the load is greater than the M crack. The cracks will start to occur, will start to appear. So from here, the M exerted by the load is less than M crack, and then here, from this point to this point, the moment exerted by the load is greater than the M crack. Because M crack is what? Let's say, what's M crack? M crack, sorry, right. So M crack is actually, it has a function of the modulus of rupture multiplied by the inertia of the section divided by y. Y is the distance between, from the neutral axis to the tension side. So let's do it as diagrams for explanation purposes. We have a beam section here, right? Here will be the neutral axis. This is Y. From the surface of the beam till its centroid. This is called Y. When the tensile stresses in the bottom or at the bottom of the beam occurs, then that means it reaches the modulus of rupture. That means the cracks or the moment or the stress applied on the beam is started to be more than the properties of the concrete for tension, because modulus of rupture is we're talking about tension, right? Take an example. Let's take an example. Say that we have a beam here, right? That is 12-inch wide and 18-inch deep. The properties of the beam is, let's say, FC prime is 4K PCI, and the moment exerted by the load is 25,000 or 25 kilo foot. Is the beam cracking? In which stage is the beam? Is it in the M crack stage or before, or it reaches the surface? So let's calculate. We have two ways to calculate it. Either, first way, to calculate the stress. The stress exerted by the load or the moment, the stress is a function of the moments. So the equation of the stress is moment, which is this one, multiplied by y, which is half of the 18, as we explained here, divided by the inertia, 25,000 multiplied by 9, 18 over 2, divided by I. I is actually B times H cube over 12. Anyway, if you do the math, it's equal to 463 PCI. All right, from the ACI code formula that we talked about in the earlier slide, we can calculate what's the rupture, right? Because the rupture is just a function of FC prime. So it's equal to 7.5 radical FC prime. That gives you 7.5 radical 4,000. It's equal to 47, if you do the math, 474 PCI. Since F rupture, or the modulus of rupture, is greater than the stress exerted by the load, this indicates no cracks, because the load didn't even reach the capacity of the tension exerted by the beam. Or we can do it in another way. Calculate M crack. M crack, what's the equation of the M crack? We just calculated it. It's the rupture, which is here, 474, multiplied by modulus, the inertia, which is 18 cube, because I'm just gonna write 18 cube because here we canceled 12 and 12, divided by 9. It will be, if you do the math, 307, 152 inch pound. That is equivalent to 25.6 K-foot. Since M crack is greater than M, that means no cracks. All right. We reached the end of this session, but next class we're going to talk about what's after M crack. So the loads persists, and then we'll move to M service, where the steel is taking the load, but it's not yielded yet. And then we'll move to the other stage where the steel is yielded and the tensions and the concrete here is destroyed. And then we're gonna talk about, this is the analysis, and then we'll move to the design. But it's important to know the fundamentals of this. Actually, I forgot to mention the concrete generally, even if it didn't crash, in tension, it's so weak. So in design, we consider it as 0. We are 100% asking, or just 100% depending on the steel to take the tension, not the concrete. Hope you guys enjoyed this video. This is a quick introduction about the principles of design. And thank you so much for watching.